Hello everyone, and welcome to another remote sensing lecture video. And in this lecture video, I want to begin talking about what are called spectral response curves. Now, let me make sure I don't accidentally cross things out here. Right, before we get into examples of what a spectral response curve looks like or what spectral response curves are, I just want to take a second and sort of set the scene for what we're talking about. So, up to this point, we've described the ways that electromagnetic radiation can interact with an object. And if any of this seems completely foreign to you, I encourage you to go back and rewatch the electromagnetic interactions videos that we have done previously. So what we sort of covered is the idea that light is being emitted from the sun, right, at a variety of different wavelengths, right, ranging from all the way through gamma, all the way up through radio waves, right? But the bulk of that radiation is in the sort of short wave wavelengths. So things like ultraviolet, visible, near infrared, and shortwave infrared, right? The wavelengths that we care most about in remote sensing. And so we sort of said that once those wavelengths are emitted from the sun, right, they hit the earth and they're either reflected, transmitted, or absorbed, right? Those are the three interactions that we talked about, right? They could either be taken up into the object, passed through the object, or bounced off of it. And we said that the remote sensor, right, in this case, is detecting that radiation that was reflected off, right? It hit the surface of the earth, it bounced off, and then it was detected by the sensor. You know what, actually, let's go ahead and just quickly draw that, just so we sort of have fresh in our mind the diagram we're talking about. So we have Earth, right? We have our sensor. We have our sensor. We have the sun. And then we have energy that is coming from the sun, hitting the earth, bouncing off the earth, and hitting our sensor. Right, and this is reflected. This is sort of the concept we spent an entire week delving into detail on. What I want to make clear here, and this is very important for the idea of a spectral response curve, what I want to make clear here is that this reflection, right, the amount of energy that is reflected, right, this reflection, right, this is wavelength dependent, right, wavelength dependent, right? Wavelength dependent. So this means you're going to have a different reflectance in blue than you do in red. And this principle right here, right, the fact that reflectance is different, is wavelength dependent, is exactly why things like your clothes actually look the color that they do, right? For example, if you're wearing a blue t-shirt today, or blue jeans today, right, the reason that your jeans look blue is because the dye pigment in your pants is interacting differently with the blue wavelengths than it is with all of the other colors in the visible spectrum, right? That dye is absorbing the reds and greens and reflecting the blues. So you see your eye is perceiving your blue jean as being blue. Okay. So I know this was a bit of a preamble here, but what I really want you to get away from this is the stuff that we talked about previously, right? This idea of reflected energy being detected by the sensor, whether that sensor is a satellite or it's your eye, is that all of those principles are wavelength dependent, right? They behave differently with ultraviolet radiation than they do with blue, than they do with green, than they do with red, than they do with near infrared, right? They're going to be wavelength dependent. And so now we can take that idea that this concept here is wavelength dependent, and we can make a nice graph of it. Okay. So just like any graph, right, we need to have two axes. We have our y-axis here, right? This is percent reflected. This could also be radiance, right? And the difference with radiance is the energy coming off. Percent reflected is if you normalize that by your radiance, right? So this could be either one. It doesn't, it matters, but for the sake of this context, right, you're going to see both of these being talked about. So this is our y-axis, right? The percent reflected or the radiance. And then on the x-axis, right, this is wavelength. Typically, we will see them, this will often be written in nanometers, right? So down here, this might be 400 nanometers, right? So this would be blue, just to sort of recap our discussion on the electromagnetic spectrum here, right? And this may go through all the way, maybe you'll see it go to, let's just throw a number, say 1,000 nanometers right over here, right? So this would be NIR, right? This would be near infrared. And what you're going to see here is we can measure the percent reflectance or the radiance of an object at every wavelength in this region, right? So what I'm going to do is I'm going to draw an example, right? So a typical example you'll see is something that looks kind of like this. Well, actually, let me be a little more accurate here. Right. And so this right here, right, this shape right here, this is very typical of vegetation. Right, and you don't necessarily, you can just kind of believe me for now. this is, if you were to Google spectral response curve vegetation, you would see something that looks very similar to this. Okay, so let's just take a second here and let's deconstruct, right? Let's deconstruct what we're looking at. Okay. So again, to recap, right, our y-axis is percent reflectance. So that means that the x-axis is wavelength, and you can go through and you can say, sort of interpreting this line here, right? So in the blue region, right, so we're just going to say, you know, roughly speaking, again, roughly speaking, right, this region right here is blue. Right, so if we were to interpret this graph, right, we would say, well, vegetation has a pretty low reflectance in the blue region, right? So then we would say, okay, well, this region over here, right, this is going to be, you know, approximately, you know, 600 nanometers. This is green, right? Again, I'm just sort of recapping the regions of the electromagnetic spectrum. And you'll say, okay, well, the reflectance is slightly higher in the green. And then we have next to that, you know, we have red. So this would be, you know, approximately 700 nanometers in the red, right? And we'll say, okay, well, then the reflectance goes kind of back down in the red. And then, you know, obviously, again, you know, from here to here, right? This is all that, you know, this is, you know, 700 to 1,000, right? This is NIR. And so we would say that for vegetation, right, they have a particularly high reflectance in NIR, right? I guess we should label this. This would be 0, and this would be 100%, right? So again, what we're showing on this graph here is we're showing reflectance or radiance, depending on what you have, as a function of wavelength. And we can use this, and we're going to talk a lot more about how we actually use these things, but just we can interpret this, right, as a way of seeing how does an object, right? In this case, we have vegetation, we have a leaf, for example, right? How does the spectral reflectance, right? How does reflectance change for this leaf as a function of wavelength? And you can see that we sort of broadly can interpret, right? In the blues, it's kind of low. In the greens, it's a little bit higher. It drops back down in the red regions, and then it skyrockets in the NIR. Okay? And again, if you were to Google vegetation, I didn't just make this curve up. But hopefully that makes sense. Again, we're going to go through a lot more examples of these, but hopefully this makes sense. Just the idea that what we're doing here is we're explicitly describing reflectance as a function of wavelength. And we do that because, again, those interactions with matter, right, transmission, reflection, absorption, right, those are wavelength dependent. And we can use that to literally just create a graph that is a function of how does reflectance change with wavelength. And this idea is going to be fundamental. And again, I'm going to say this again. This idea is going to be fundamental to pretty much everything else we talk about in this course, right? The fact that we can use different regions to differentiate different objects from each other because they have different properties depending on the wavelength you're looking at. Hopefully this made sense. Again, we'll go through some more examples. But as always, please reach out. Thank you.